right. Hello. So I start recording. Okay. Today we are going to talk about texture mapping, uh, which will allow us to give variable or varying reflectance coefficient for the diffuse component over the surface of an object. So instead of having a red sphere, we will have spheres, for example, for the Earth. We will have the different part of the sphere will have different color. In other words, different diffuse reflectance coefficients. You can also replace specular or other parts, or you may directly replace the color with the diffuse color component, but that we are going to see that doesn't give natural results. But our goal will be, instead of having fixed color over the surface of an object, texture mapping, we'll be able to map images to the images of arbitrary that contain arbitrary pictures in them, and we'll be able to map this 2D image onto a two-dimensional manifold. It may be as simple as a sphere like this, or it may be as complicated as an object with many triangles. It may contain thousands of triangles, and we will be able to still map a single image over those 1,000 triangles. So this is called texture mapping. All right, so today we are going to talk about this, and if after we finish this, we will talk about transformations, how to move objects, rotate, scale our objects in the scene. This is called modeling transformations. We'll see how we can do these transformations easily with the help of matrix operations. And we will use this modeling transformation. We can use them both in ray tracing or with OpenGL, which means the forward rendering pipeline. All right. So before we start texture mapping, if you have any questions, feel free to ask. Any questions about the assignment or any questions in general. I hope everything is going well with the course. So we are finishing our 5th week after these 2 hours of lectures. 5 weeks of the 14-week semester will be over, and we are almost halfway. We have finished ray tracing. After modeling transformations, we will start talking about our new algorithm, forward rendering pipeline. We will start to learn a new graphics library, OpenGL, and towards the end of the course, you will learn a new language, which is very similar to C, named GLSL. The shader programmable, basically they're called shader languages, but it's very much like C. So that's the plan for the rest of the semester. All right. Yeah, I think there are no questions. So the assignment deadline is this Sunday midnight. I hope everything is going well with the assignment. All right. So let's go ahead and start talking about texture mapping. All right. So until now, let me also have it full screen. Yeah. And put them a little bit towards right, like this. All right. So as I said, at this point in the course, we know the ray tracing algorithm. And with ray tracing algorithm, we are able to compute colors for each pixel separately by intersecting our rays with the scene objects, and then compute the color of these rays by using 3 main components. First, the illumination component, which also contains 3 components on itself: ambient, diffuse, specular. That's the illumination component, or shading component, you may say. And then we have the implemented shadow and also reflections. So in this scene, you see all of them. So we have a shiny sphere and a matte sphere, in which it's specular exponent, or it doesn't have any specular component. And this one, we can see that there are 3 light sources in the scene. We can guess maybe there are more. We don't see the back of these objects, but there seems to be 3 light sources in the scene, and we can see shadows due to these light sources. Some of these, for example, this shadow, which is a very light shadow, is due to probably just one light source. The other light sources can see this point probably. Probably this one is causing this shadow, and there may be shadows in which none of the three light sources can reach that point, so we get the pure ambient at that point. Maybe this a little bit dark, lighter shadow than this one is the case where um, two of the light sources cannot reach this point, but one of the light sources can see this point. So it may be maybe so we can get clues about the number of light sources. We see the reflections, so we have shadows. The tabletop is a reflective object. So this is right now we know an algorithm to generate such kind of images. But for realism in many computer graphics applications, one thing that people started using from the very early beginning is a technique called texture mapping. As I said, its main idea is instead of having, and the main goal is, first of all, let me say, the main goal is to increase the realism in the scene. Okay, so how can we have, because in real life objects do not have these smooth same colors all over their surface. We have a tabletop which is made out of wood. The wood has the varying color over the surface. We may have brick walls. If you have a building with walls, for example, with a brick wall, for example, brick outside, it will not have a same color. So in real life, we have objects' colors that are textured. All right, so how can we incorporate this to increase the realism in our scene? The way to do that is to have a mechanism to have different color, to assign different color at every point on this sphere. All right, so in modeling, what people do is when they're and this one, so we need a mechanism in which to map a two-dimensional image, which we call a texture. The 2D dimensional images, which are like photographs or pictures that you take, okay, you make, or the photos that you take, it could be used as these two-dimensional images, and this is called texture. And we need those textures. Actually, if you look at the texture color RGB, the color of the texture RGMB could be used as color of surface point. All right, so that's the idea. How can we map? How can we get some pixel colors from the texture image and use it as reflectance coefficients of a surface point, of a virtual surface point? All right, so this is the idea, and we are going to see how we can do this mapping. The important thing here is that we are mapping a two-dimensional image to a two-dimensional surface, but there are also other dimensional textures. For example, there are one-dimensional textures which give just changes on a one-dimensional line, and you may map it to something one-dimensional in your scene. Or you may have three-dimensional textures which indicate like CT scans. A three-dimensional texture may be like a three-dimensional object like a computer tomography or MRI. Yeah, that's a three-dimensional, like a CT scan in which there are slices, and each slice is like a 2D image, and you can try to map it to something three-dimensional on your scene. But the most frequently used, most widely used texture, when people understand texture mapping, it's the 2D version. When we talk about texture memory, texture images, we always, most of the time, almost always have a two-dimensional image mapped to a two-dimensional manifold, which is like a sphere or a triangular mesh. Our meshes or spheres will be two-dimensional manifolds, and this is what we understand by texture mapping. Okay, so here after we do the texture mapping, you look at this marble texture. It's a 2D texture. As you can see, the color is varying over the texture image, and it's a very it's used in the very early computer graphics applications because it's very cheap and effective way to change the color. So we already have an image like this. It's images do not take too much space. Just store it in some place in memory, and then after you provide some initial mappings. By the way, this mapping of texture pixel coordinates to surface points at certain landmark points, like at the vertices, it has to be done manually because we cannot. There are multiple ways. There are infinitely many different ways to map this texture onto a surface. For example, where am I going to put this point here? Is it going to be here? Am I going to map this texture at the foot of this table, or which coordinate is going to be mapped, which texture coordinate is going to be mapped to which point on the surface? It's not done automatically. It's automatically interpolated. So certain parts of the texture, we need to first provide the mapping as the modeler, as the person who builds this model, just like we determine the geometry of this object. Just like you paint it with some color, the modeler, the person who models this, also provides texture mappings to certain points, like landmark points, like vertices, or we need to first provide a mapping rule. And after that, because there are infinitely many points, imagine if this is represented like a sphere object, a mathematical representation. This is not a sphere, but you can represent the part, for example, like an ellipsoid type of object. If you have a mathematical representation in which this is continuous, there will be infinitely many points on it. I mean, even if it's made out of triangles, inside a triangle, there are infinitely many points, right? When we hit our ray inside a triangle, we treat the triangle itself also as a continuous polygon, a three-dimensional polygon. So our ray can hit any one of the infinitely many points inside the triangle. So we cannot provide mapping to every one of those infinitely many points. So what we do is we provide the mapping, for example, only for the triangle's vertices. For example, we say that, okay, this coordinate here maps to this vertex of the triangle. This coordinate here maps to this vertex, and this coordinate. We provide three coordinates, texture coordinates, and say that these coordinates map to these vertices like that. We only provide this information during modeling. Then the rest is just an interpolation problem. For example, when your ray hits somewhere in the middle of your triangle, all you need to do is you'll find its texture coordinate is going to be somewhere. Let me actually draw that here. This is my pen. Imagine one triangle's where the vertices are mapped to these texture coordinates, the red dots here, and this is how the triangle surface is supposed to look like when it's mapped. So this is the point. So when my ray hits an arbitrary point inside the triangle, in order to find the texture coordinate, the image coordinate on the texture image that is closest to this point on the triangle, we are going to use interpolation, the interpolation of the mapped vertices to figure out the texture coordinate of this one. And there are many techniques. For example, one thing that is a problem here is that the texture image is discrete, right? I mean, the image coordinates on the texture are discrete image coordinates, but the triangle, when the triangle is continuous like that, when the closest point, I mean, when your ray hits a texture coordinate, which happens to be like a floating point number like this, for example, the coordinate may turn out to be 20.4, 37.8. All right. Now, if this is the texture, we'll see the texture coordinates will be between 0 and 1, but just for as an example, I'm giving a real number here to say that, okay, which texture pixel are you going to use if these are the resulting interpolated values? One thing you can do is, one option, this is one of the algorithms we'll see, to use the nearest texture coordinate. For example, we can round these numbers. The texture coordinate 2338. Let's use the pixel. They're also called texel, by the way. I'm writing in chat box. Texel is texture element, just like pixel is picture element. The texture pixels are sometimes called texels, or most of the time we just also call them pixels. Okay, so we can actually, if this turns out to be the interpolated result, we may use the nearest pixels color to use the color. Another thing we may do is, why limit ourselves to just one texture pixel? just one texel. We can use this and somehow use, okay, so if this is where our texture, interpolated texture point falls into, using the nearest one is like, yeah, exactly. We can also interpolate nearest. Actually, what we can do is we can find the 4 neighbor pixels and we can average the texture values or the color values around it. So we can actually use some kind of a blurring, some kind of an averaging with the neighborhood pixels. These are the 2 algorithms we'll see actually. The first one is used just rounding the interpolated real value texture coordinates. If we round them, this is called the nearest pixel method. When we use interpolation of the neighboring pixels, it's called bilinear interpolation. Okay, the bilinear means that since we have a 2D surface, we have to interpolate. We have to get the average both in the row and in the column, in the both horizontally and vertically. That's what bilinear means. Like it's actually 2-dimensional interpolation. Okay, I'm going a little bit ahead of myself. We are going to come to all these in the respective slides, but just to give you an overall idea of what we're trying to achieve. Just if you have any, you may have some questions in your head, for example, at the start. Okay, how is this mapping done? Okay, our goal is to map this 2-dimensional image onto surface colors, but how do we do that? Is it automatic? As I said, the main thing I want to say here is that first part, the modeler maps the texture coordinates, certain texture coordinates are mapped to certain landmark points. If it's composed of triangles, the triangle vertices are mapped to texture coordinates manually. So it comes actually with some of the models you download from websites like TurboSquid. It comes with texture coordinates, just like our XML format for the assignment contains vertices. Each vertex has coordinates, XYZ coordinates. Objects have materials. Just like that file, an additional attribute of a vertex could be its texture coordinate. And texture coordinates usually are given, actually the texture space, sometimes indicated by the UV space. Okay, these are the XYZ indicate, so the variables XYZ are used to indicate the geometry, the 3-dimensional spatial coordinates of a vertex. This is also an attribute. OpenGL especially, I mean, the graphics libraries are getting so general purpose that, I mean, we do not associate these, the attribute of a vertex can be anything. For example, the coordinate of a vertex is just one of its many attributes. It's another attribute, maybe this 2-dimensional vector, which is this texture coordinate. So for this vertex, we may also associate a 2-dimensional coordinate, u and v, in which u and v are between 0 and 1. Okay, they may sometimes be larger than that. We'll see. For when we are doing tiling, we are using the same texture, but given a single image, its coordinates will be something like this. Okay, this is the u-axis, this is the v-axis, this is 0, 0, this is 1, 1. So we will use these normalized coordinates for any given texture image. It may be rectangular, it may be very large, it may be very small, but for a given texture, we will use these normalized coordinates for that texture. A single texture, its coordinates will be, coordinate span will be like this, and we will be, for each vertex here, we may associate a certain UV coordinate to that, and these UV coordinates are real values. So we are not doing the initial mapping of the vertices to these texture coordinates are not discrete. They are not integer coordinates. The UV coordinates are real valued numbers between 0 and 1. So if this image contains nx and ny number of pixels, in order to find the correct texture coordinates in terms of integer, what we do is we multiply nx with u, and we round it, for example, for the nearest pixel value. So if you multiply, for example, if u is 0.7 and you have the resolution of 1000 pixels here in a row. You just multiply 0.7 with 1000, it gives you 700. So the pixel coordinates should be around 700. Okay, so this is what these u and v coordinates, since they're between 0 and 1, based on your image resolution, you have to multiply these texture coordinates to get the integer texel coordinates. All right, so these, as I said, these are given as just regular in the modeling stage. These are provided, and this certain modeling programs like Blender gives you utilities to do this process easier. For example, instead of manually just picking up texels and then putting there are tools like texture painting. You have a texture, you just for example, just like paint brushing over a surface, you just choose as your color the texture, and you can paint texture over a surface. So it's really nice actually. You can select different, you can stretch different parts, and then underlying mathematics will be individual mapping of vertices to these UV coordinates will be done by your modeler program. All right, so after texture mapping, we're going to have nice spheres or other surfaces, which will give us nice looking graphics results like these. And another thing is, so this normalized coordinates are needed because texture images may be of different sizes, the objects may be of different sizes. We may sometimes want to map the same texture over a small sphere, medium sphere, or a large sphere. So we need a uniform way so that any object can be mapped by any texture. So, and this uniform way is to associate this UV. Actually, I have indicated the UV coordinate system wrong. The V coordinate is actually towards down. So this is 0, 0, and this is 1, 1. I thought it was the other way around, but so this is the 0th row. So it doesn't matter. I mean, just invert the V axis. Okay. The only thing that is different from my case, so this is like a left-handed coordinate system, not right-handed coordinate system, in which the V is down. So V is inverted, but the idea is the same. We have a coordinate system where U and V are within this interval, 0 and 1. And in order to map a certain point on this texture image to our geometry surface, a point surface in our surface, we need to parameterize our 2D surface if you want to do something mathematical. Or instead of parameterizing your surface, if you have triangles, for example, you need to map the vertices. So for spheres, we can actually do this mapping automatically. If we can have a mapping between the surface point and these UV coordinates automatically. So I'm going to show one way to map a surface point XYZ on a sphere to UV coordinates. Okay, so although the surface point is three-dimensional XYZ coordinates, it's actually you know that a sphere is a two-dimensional manifold. So any point on the sphere could actually be indicated by two values. So with just two values, you can uniquely identify where you are on the sphere. That makes it a two-dimensional entity, actually, the surface of the sphere. So any entity that is living on the surface of a sphere is living on a two-dimensional world. So, and these two parameterization are like the latitude and longitude information. So we can actually, instead of using the equator as the 0 latitude, so latitude is how far you are away from the equator, but we can have our own parameterization here. So here the latitude is defined as how far you're away from the poles, the North Pole. Okay, so let's define this angle theta as, so this is the surface point. So when we draw this vector from the center of the sphere to our surface point, which has a radius of r, Okay, so it will be making two angles actually. You can think about it like this. So if you have a sphere, let me have this. So if this is my half sphere, so depending on where this point is, there are two things: how far you're away from the North Pole, that's one angle, and how far you're away from Greenwich. So if the center middle of the sphere is like Greenwich, you can move towards the western hemisphere or eastern hemisphere. So how much you're away from Greenwich is the angle phi here. So this can be represented by two angles, theta and phi, and given two angles. And by the way, if you look at how theta ranges, the range of theta is between 0 and pi, or 0 and 180 degrees. If you're using radians, it's between 0 and pi. If you're using degrees, theta ranges from 0. When it's 0 degrees, you're at the North Pole. When it's 180 degrees, you're at the South Pole. Okay, so when it's 180 degrees, when it's 90 degrees, theta, you're at the equator. So theta ranges from 0 and pi. On the other hand, phi here can have 360 degrees or 2 pi. Okay, so because you're so each of the, you can think of this phi as the circle at a particular slice. So phi tells you where you are on that particular circle. So for this XYZ point, actually, we are currently in this slice, and this is the angle phi is telling us where we are on that sphere. If I couldn't draw it nicely, but imagine this point is on this circle. Phi tells you where you are on that circle. So this phi is just using the circle equation, all right? And theta is which theta determines which slice you are currently on from the equator. And here at this point, as you can see at the North Pole, we have a singularity. Our circle becomes a single point. Okay, so that's like a singular point here, whatever you're doing. So what we will do is, our goal will be to map each of these slices of circles to a row in our 2D world map. Look at this. This is, think about this. Look at this line that I just drew. It is like if you consider this as the equator, this will be this row, this single row here will be mapped to a certain slice, and then the second row, which contains also the same number of pixels, will actually be mapped to a smaller slice. And here is the singular point. The first row here, which contains the same amount of pixels as the one that is in the equator, is actually going to be mapped to a single point. Okay, as these circles get smaller and smaller like this. Okay, so this is what we'll try to do. And this, if you look at these equations, the XYZ coordinates could actually be given by the circle equation by using this theta and phi. So your y coordinate, how far you are, is just determined by theta. Rcos theta gives you your y coordinate. And your z coordinate. If you look at x and z coordinate are your coordinates, two-dimensional coordinates on the xz plane. So cos phi, sin phi. So this becomes like the radius of the slice at parallel to the xz plane. That becomes like the how it will give you the slice actually. Yeah, that's correct. So it will tell you how far it will tell you the radius of the slide. Yeah, if you look at this, is it rcos theta? It seems like, oh, okay. If theta was here, okay, if theta was this one, it will be sine theta, right? I mean, if theta was this figure, this, but it's not this. Theta is defined. Actually, theta is defined like that. Is this equation correct? I would say if this is r, I mean, the radius of this sphere at this point seems to be not cos theta, but r sin theta. I'm not sure. I'm going to take a look at this. I mean, this is the radius of a sphere, right? I mean, this will be the center of the sphere at this slice, and this is a point on the circle. So this is a circle, and at this point, this is the radius. The radius is getting smaller and smaller, and if it is cos theta, when it is 0, when the angle is 0, we should have a 0 radius, right? But cos theta, when it becomes 0, it's 1. The radius is going to be r. So this theta is defined. So there's something wrong on this slide. Yeah, here the thing is, we should use sine theta here. If you use sine theta, if theta is defined like this, if you use sine theta, when theta is 90 degrees, it will be 1, and this will be exactly equal to r, and it will get smaller and smaller. Okay, yeah, r, it should be r sin theta. That's the radius, but its y coordinate is r cos theta. If you look at, oh yeah, you're right, the y coordinate is not the radius. The y, yeah, actually I'm reading the slide. We already have r sin theta here. That's the radius. Thank you for correcting me. So I was interpreting the picture correctly. The radius really is r sin theta, and it's written correctly here as r sin theta. But if you look at the y coordinate, which tells you how high, so the y coordinate is not your radius. Y coordinate is how high you're away from the equator. So it should be 0 when you're at the equator. So therefore, when theta is 90 degrees, it will be cos 90 will be 0, and it tells you that your y coordinate is 0. You're right at the equator, and your y coordinate will be equal to r. You will be r distance from the equator. That's your y coordinate, and theta is equal to 0. Okay, thank you for that correction. But it also makes help us understanding this parameterization. Okay, this one is just one of them, which is your y coordinate. Just depends on theta, how far you're away, the angle from the equator. After you have that, it gives you a circle. The rest is just a circle equation. So this is the radius of the slice, and this is our regular 2D parametric circle equation. R cos phi, R sin phi gives the xz coordinates on the circle that is parallel to the xz plane. Okay, so all of the points on this slide will have the same y coordinate. I hope it's clear. Thank you for correcting me. All right, so also in practice, we can use using these z and x coordinates if somebody gives you z and x coordinates of the sphere. So the problem we will try to solve is, we have a ray here, it hits a point on the sphere. So we know its xyz coordinates. So given the xyz coordinates of a sphere and its center coordinate and its radius, if we know the radius of a circle that our ray hits, if this is the point P that our ray hits, given the xyz values, our goal will be to figure out these two parameters, theta and phi. Because by using this theta and phi, these two angles, we will provide a mapping from these two angles to the UV texture coordinates. That's our goal, because these are the two parameters that we will be using. So here, if you look at this picture again, for example, if it turns out to be theta, if theta becomes equal to 90 degrees, when theta is equal to 90, we need to get this texture coordinate. When theta is equal to 0, we need to get this texture coordinate in terms of its y coordinates. And based on what phi is, okay, we need to figure out where we are on this row, which column we are on this row, by looking at our phi value. By using these two theta and phi values, the next step will be to convert them to texture coordinates. But the first problem we try to solve, given an xyz value of a point our ray intersect with on the sphere, what are these theta and phi values? So, and we can find that by using these two equations. So it will by using the same parameterization. So by using these, we can write these equations in terms of theta and phi to get to find those two values. And yeah, theta is in between 0 and pi, and phi is in between minus pi and pi. So it spans 360 degrees on the circle, while theta is between 0 and pi. Okay, so and these are the values that these values will return. So, okay, so our goal will be to wrap the image such that it's going to be like this between. So this is exactly repeating what I said. So we are going to map these rows to determine which slice of the circle we are on, and this one, the yellow one, is going to be mapped to a particular circle there. Okay. So the u and v values, if you want to convert, so the angles that are between 0 and pi will be between 0 and pi. But our u and v values are between 0 and 1, so we need to normalize them. Since this is between 0 and pi, if you divide theta by pi, v will be a coordinate between 0 and 1. So your v coordinate, which was between 0 and your theta value was between 0 and pi, if you normalize it by dividing by pi, it will be between the v coordinate will be between 0 and 1. And also your phi value, which was between minus pi and pi, you also need to get it between 0 and 1. What you do is you add pi to it. Okay, you first make it negative. Okay, you also and you add pi to it, and you divide by whatever when you add pi to it, the minus pi becomes 0, and the largest value you get will be 2 pi. So the value you get if you do this, the value will be between 0 and 2 pi, and normalizing with 2 pi, you will also get yourself the u coordinate between 0 and 1. So this is how we get u and v coordinates of a particular xyz point on a sphere. And after we have the u and v values, as I told you in the earlier slide, we need to multiply these values between 0 and 1 with the resolution of the image to get the pixel coordinates. So let's see how we're doing on time. So we still have 15 minutes. So this is how we get the pixel coordinates on the texture image. And this is a texture image width, texture image height. And since at the end, after you multiply it like this, I and j can be real valued fractional numbers. As I gave the example, 23.4, 37.8. So we can have them as fractional. So we need a mechanism to make these ij coordinate discrete. And that's the two strategies that we have mentioned. Choose the texel color using a suitable interpolation strategy. We can interpolate by choosing the nearest neighbor. That's the easiest case, in which we just round. Whatever ij values you end up with after you multiply your uv coordinates with nx and ny, you just round them. It will give you a single ij coordinate, and you just fetch that from your texture image. That becomes the color of XYZ. So that's actually using the texture color directly as the surface color. Okay, so this strategy, as you can see, is using the texture color and putting whatever texture image color we have directly on that pixel. But what we can do is we can do something better. Why not also consider the interaction of this surface color with the lights around it? Why do we just set the pixel color directly to the texture color? Why don't we shade it? If it's, for example, seeing that if that surface normal is not toward the light source, our texture image, that part may be darker, or if it's directly pointing to the light source, it may be lighter. So just instead of using this texture color directly as the pixel color at that point, what we can do is we can use it as the diffuse reflectance coefficient and compute the color. So the diffuse reflectance coefficients right now, which is just the constant for all the sphere in your assignment 1 input file, imagine those reflectance coefficients are changing all over the surface. You will basically be doing texture mapping if you can do that. The second technique is called bilinear interpolation. And as I said, it's just like finding the four closest pixels. So we find the average, we first find the four closest neighbors, and we take the average of these four texture four texture values, colors, and assign it to our ij, or to that texture location, to that point that our array intersects with. So we first find the nearest one. So PQ here is the same as, it's not the nearest one actually. We are not doing rounding. We are actually using the one which is to the left and down. Okay, so since we are using floor here, so we just the closest pixel center that is to the left and towards the bottom. All right, so this is the closest pixel center is PQ. Then what we do is we fetch these four other pixels, which are PQ plus 1, P plus 1Q, and P plus 1Q plus 1. So these are the four neighbors we look at. Okay, after we find the closest pixel that is to the left of it and towards bottom, we add these three, 1, 2, 3, and this is the original one. We can call it the 0th one. We add these 3 pixel coordinates too by just adding them like this. And here it's called interpolation because they're not the averaging of these 4 pixel values, texture colors, is not done equally. It's a weighted averaging of these texture colors by actually using the distance of our point to each of these texture coordinates. And it's first done, as you can see, that it's done by 1 minus dx, 1 minus dy, is if dx and dy is 0, if this is exactly on this point, what will happen is that it will directly, if this point happens to be at the center of a pixel, what will happen is that dx is going to be 0, dy is going to be 0. Dx and dy are the distances. Dy is the vertical distance. Dx is the horizontal distance to this left and bottom pixel center from our point. Okay, so dx is actually just the difference. If you look at what dx is, it's the difference I minus floor I. Okay, this becomes dx. Dx is this, dy is j minus floor j. Okay, so both in this case dx and dy are always non-negative, right? They can be 0. If I and j are integers, they can be 0, but if not, the floor is always going to get whatever number you have here, real number you get here, floor is always going to make it smaller. And if you subtract I from that, it will be a positive number. Same with j. So dx and dy are these distances. Oh, actually it's written as right here. I didn't need, it was already here. Sorry about that. I just repeated what's written here. So then we just use these two values, the distances, as weights in our averaging. The farther away you are from a point, the smaller the weight. All right. So this is how bilinear interpolation is performed with a weighted average of the 4 nearest pixels. And here are some figures that show the difference between by the way, nearest neighbor is much faster than bilinear interpolation. As you can see, just use one round operation. Bilinear interpolation is slower, but it gives more smooth results, especially at if you have a very high resolution surface. If you're mapping a low resolution texture onto a large surface, you will notice the difference between nearest neighbor and bilinear interpolation. But if your texture image is really high resolution and you're mapping onto a smaller surface, you will probably not notice the difference between these two methods. So you can use nearest neighbor if you have a higher texture resolution. But using bilinear interpolation is suggested if your texture resolution is not that, your texture image is not a high resolution image. So here are differences. I'm just switching between the two slides. So this is in bilinear. As you can see, it's smoother. If you can quickly go, yeah, you should have this in the PDF. The PDF slides are available on OptiClass. Ozuca uploaded them. So if you just switch between these two slides, you may notice the difference slightly. This is nearest. There are more zigzags at the edges of these checkerboard pattern. You can see more zigzags in nearest neighbor method, and in bilinear it's a little bit more smoother. And I think this should be a movie here. I can just pointer options. Just, yeah, so these are the two movies. Let me just play them both. This is the nearest neighbor. As you can see the zigzags as it's rotating like this. The interesting thing is the zigzag points where the zigzag is, they stay constant. The image is like moving towards it, because for this XYZ coordinate we always get the same floating point number. So the texture coordinate may be changing, the zigzag point remains the same. And if this is the other one, it's more smoother. One zigzag point like per square. Here there are, it's also just like one. But sometimes the zigzag is, its height is smaller than this one. So it's smoother. So let me play it again. But the notice is, I mean, you may just, if you think that the difference is too little to notice, I would suggest using nearest neighbor, because it's much more efficient than bilinear. And also you may have the choice between nearest neighbor and bilinear interpolation as your gameplay settings or graphic settings in a game. Okay, if you're playing a game, there may be some advanced graphics options that you may select in the game. And in the texture, sometimes it says use low, high resolution texture. There's also, you may change the texture resolution as one of the parameters. And one of the parameters in some games may be to choose between nearest neighbor or bilinear interpolation to do your texture mapping. And the texture color, okay, we may either directly, so this is the case, we still have the specular as usual, but this is the version in which texture color immediately replace the diffuse color. Okay, so there are several options. We may replace the entire shading color with, even with no specular like this. We can blend it with shading color by adding as a new option, just like the reflection part. For mirror reflection, we were adding it as the fourth parameter. We can also blend the texture color as a new fourth attribute, or we can replace the diffuse color completely, or we can replace the diffuse reflectance coefficient. And diffuse reflectance coefficient, changing it with diffuse reflectance coefficient is just, instead of using this KD, we just use the texture color. And since the texture colors are between 0 and 255, and KD values were between 0 and 1, we can simply do a floating point operation here to get a real, I mean, if your texture color is also integer, don't forget to explicitly cast one of these to floating point, because otherwise your KD will either be 0 or 1. Okay, in order to get, I mean, in C, if you're doing an integer division, ensure that you're doing a floating point division to compute this KD, which will be between 0 and 1. Actually, it's a three-dimensional vector, which each of which dimensions are between 0 and 1. All right, so, and here is the difference between these two. If you directly replace the diffuse color of your texture, it looks like this. As you can see, all of the blue parts, the diffuse part, the lighting amount is exactly the same all over the sphere. But if the light is in this direction, you should get darker blue in these regions. So when you replace the KD reflectance coefficient, you get a much nice looking sphere, which is texture mapped. And here is a video, and I will, after this video, I'm going to have a 10-minute break. So you can also, this is ray traced. You can generate lots of texture mapped images of the sphere by rotating your sphere around its center, and you can just combine them one after another to produce a video like this. And texture mapping is very efficient. If you just have one sphere in your scene, generating this scene is very efficient, and you can even have some kind of real-time ray tracing. If instead of writing out ppm images, if you use some kind of a library which gives you a graphics context and you update that graphics context in real time, you may even get an interactive graphics application like this. All right, so before starting texture mapping triangles, I'm going to, let's have our break now. It's break time, so let's have a 10-minute break, and after the break I'm going to continue with texture mapping. Now this time we are going to see how to map texture coordinates onto triangles. All right, see you all in 10 minutes.